Okay, so let's do this problem. I'm going to do a little bit of shortcut. Oh, I forgot. This is 3 meters, 4 meters, and 3 meters. So I'm going to assume at A, which is over here, I'm going to draw my positive shear at A up, and of course over here positive shear at D is down. So let me go through this the statics to find these reactions. So I'm going to sum moments at A, make sure it's in equilibrium. So when I look at all my forces about A, all the applied forces are going to create negative moment. In fact, I'm going to go ahead and make a concentrated equivalent force for my distributed load, which will be, what is that, 10 times 15? 150? That sound right? Anybody out there?
Yes.
Oh, yeah. Okay, good. Nonverbal communication. You guys are into that? Of course, nobody says anything and just shakes their head. Great. Okay, so the first one will be 40 kilonewtons times a moment arm of 3 meters. The concentrated equivalent force is 150 kilonewtons times a moment arm of, let's see, it'll be half the distance, or what is that, 5? And then the 80 kilonewton force, its moment arm is 7. And then even the shear force, the way I've drawn it, creates negative moment, and it has a moment arm of 10. So hopefully when you find the shear at D, it has a negative value. I think I remember this is 143. Does that sound reasonable?
143 or 147?
143.
What does that equation give us? Somebody calculate that real quick. And while you're doing that, I'll go ahead and say that I'll sum 140 what? 3. So then we'll sum forces in the y direction, make sure we have 0. So I've got my shear at A up, got my shear at D going down, and then all my other forces, 40 kilonewtons, 150, and 80. So I should be able to solve for the shear at A. I think it comes out positive 127. Does that sound familiar? So that's the easy part. So based on that, I'm now going to make a template to help me draw the shear force and bending moment diagram. So there's the outer boundaries from A to D. For the shear diagram, I'm going to establish a x-axis and a positive shear, and all my units for my numbers will be in kilonewtons. So what is the shear at A? According to my calculations, it's 127. So I know it's positive 127. What is the shear at D? According to my calculations, it's negative 143. So I kind of know where I'm starting, and I know where I'm going to end. There's a couple other interesting places that we need to point out. This applied load here at 40 and 80, what's going to happen to the shear as we go from the left side to the right side past each of those forces? We're going to have a drop, right? So that's a good place to also include that in our template. We know there's going to be a dramatic change in the shear, so I'll add that in. So now I'm ready to apply my relationships. I know the change in shear is the area under the load diagram. So what is the change in shear over the first 3 meters? It's starting at 127, so the change in shear should be the area under the load curve, which is what? It's a rectangle, base 3 meters, height 15, so that's a 45. And is that positive or negative change? It's negative. The load is down, so it's negative. So what's 127 minus 45? Everybody buy that? We also can figure out or determine the shape of my shear diagram by looking at the load. If you look at the load, it has a constant value of minus 15. So this is a negative slope. And if we actually measured that slope, it would be minus 15. So that first section is trapezoidal. That probably looks familiar, doesn't it? Now what happens is I go from just to the left side of 40 to just to the right side. The change in shear is negative 40. So 82 minus 40 is 42. See that? So we're at 42 just to the right of that 40 kip load. So what's the change over the next part of the region? Well, it should be the area under the the load diagram, which is what? 15 times 4, which is 60, right? So what's 42 minus 60? Negative 18. What's the shape of that curve? Well, according to our relationship, the slope of the shear diagram is the load, and what's the load? Let's see, it's negative 15, negative 15, it's always negative 15. So constant slope would have the slope of negative 15. So these two slopes are the same. They just kind of take a little step down. Now what happens is I go from the left side to the right side, and I pass by that negative 80 kilonewton force. It should drop down 80, right? So that's going to be right about there, and that's going to be 98. What's the change in shear between between these two? The last. Well, it's 3 times 15. It's negative 45. Hopefully, if you take negative 98 and you subtract 45, you get negative 143. So we matched. That's great. And what's the slope? It's constant because the shear is constant, and it's negative 15. So that line is the same. So really the slope of all those lines is negative 15. They just take a little jump as they cross over. But now something unique has happened. Our shear now has a 0 value. And we need to add that to our template. Why? Because we know that when the when the shear is 0, the slope in the moment diagram is 0. And the 0 slope means you probably got a max or a min. In this case, it's going to be a max. So far, so good? Now, if that's going to be important to us, this is the part I really want to talk about today. What's this distance here, x? Well, don't give me the answer. How do you find it in general?
Similar triangles?
No. No. Follow the equations. What is the change in shear from 42 to 0? Not that hard. You start at 42, you go to 0. What's the change in shear? How do you go from 42 to 0? What do you have to do? You have to subtract 42. Simultaneously, if you go up and you look at the area under the load curve, what is the area under the load curve? It's a rectangle. It would have a base of x and a height of negative 15. So that means simultaneously the area under the load curve is negative 15 times x. Right? Those two things are equal. So that means I get an equation that says negative 42 equal negative 15 times x. Solve for x. And what do you get, Mr. Maxey?
2.8.
2.8. Now, are there other ways to get that? Sure. I like this way because it keeps using the same things that we know. You've used these things now repeatedly. Why not continue to use them? Don't muddy the water by throwing in something other things, similar triangles, or write an equation. Why do that? Just use what you know. So if this is 2.8, is it 2.8 or 2.3? What's 42 divided by 15? It's 2 something. 2.8? So this is 1.2. So now I have all the dimensions I need. So let's add it in our positive axes for our moment diagram, and all of our units will be kilonewton meters. So what is the moment at A? It's an external roller, so it's 0. What's the moment at D? It's an external pin, so it's 0. So I know where I'm starting, I know where I have to end. Now we get a different set of relationships, similar, but different quantities. So now I know the change in moment is the area of the shear diagram. And that the slope of the moment curve is equal to the shear. So that's why this is important. Since the shear is 0, that means the slope is 0, then we're probably going to have a maximum value right there. So what is the change in moment over the first 3 meters? It's the area of the shear diagram, which is trapezoidal, right? So the area of a trapezoid, you just simply average the heights and multiply by the base. So what is that? The average height is 104.5, and then times 3, I got 313.5. Did you guys get that?
313.5.
And that's a positive area, so it's a positive change. What's the slope look like? Well, according to this, it's the value of the shear. So the shear initially is positive 127 and drops off to positive 82. Those are pretty high slopes.
So it's going to be like real steep at first and then kind of flatten out?
Well, not really flatten out. The slope is still 82. It's still pretty steep. It's going to be difficult for me to draw this to scale, but I would say it maybe looks something like that. Right? And I'll emphasize that by showing that I've got a kind of a big slope that maybe is getting a little bit smaller.
On the test, we need to put those emphases on there?
No. That's just for your education. It helps me keep track of it. The most important thing in this is just the general shape and the values, that you have the max and min and all the transitional values, right? So I'd be more concerned that you get the 313.5 correct and just some kind of shape. I mean, you're not going to draw these to scale.
As long as it's curved, we're supposed to be curved.
As long as the curve is you got the right concave or convex shape, that's all that I care about. Because what's going to happen now, as you move to the next piece, right? Well, you can see the slope drops off. So this slope, as it leaves, is going to come off in a different slope. This is 82 on one side, the left side, drops down to 42 on the other side. So it's going to be like a little kink in your curve. And what's the change in the moment? Area of the shear diagram. So what's the area of this part of the shear diagram? 42 times 2.8 divided by 2. What's that? I got 58.8. Did you guys get that? Did I do that wrong?
No, 58.8.
So we just add that to 313.5, and I get 372.3. You guys get that? So the slope is given by the shear. The shear just to the right is 42, and this is the important part that I wanted to pick out. It goes to 0. So I know the slope here is 0, and I know here the slope kind of kinks. So your curve takes a little bit of a bend there. Can't really see it, but that's the idea. If you just draw something that kind of looks like that and you have those two numbers on it, that's all I care about. Now what's the change in moment over this next 1.2 feet? What would be the area of this part of the curve, which is 18 times 1.2 divided by 2. I got 10.8. That's negative area. So you're going to start with your 372.3 and subtract that. You get a little value here of 361.5. Does that sound familiar?
Yes.
And its shape is going to be given by this relationship, which is the shear. The shear starts off at 0 and ends up being relatively small negative. So again, that kind of tells you how the curve is bounded here. So the change in moment to finish this off ought to be the area under this big trapezoidal section here, varying from negative 98 to 143. So what's the area of the trapezoid? Well, I'll just average those two. And I get the wrong answer. Let's see, 98, 143. That's 120.5 times 3. Hey, what do you know? I get 361.5, so that brings me to 0. What's the shape of the curve? Well, it starts off at a negative slope that's bigger than the previous one, so it's going to turn down a little bit. So it's going to start turning down, and it's just going to get bigger as we go down the line. So your curve does kind of take a kink and go down like that. So when you draw it by hand, you're not going to see those transitions in slope very well. If you drew it to scale, you'd probably see a bump. But what do I care about that? I don't really care that much. All I care about is the final question is, where's the maximum moment in the beam? Well, it would be here at 372.3, and where would it occur? It looks like it would occur 3 meters plus 2.8 at 5.8 meters from A. So I might ask you, what's the maximum moment? And you would tell me that it's 372.3 kilonewton meters, and it occurs at x equal 5.8 meters from point A. What's the maximum shear? Negative 143, and occurs at D. So this is the part I wanted to talk to you about how to find these. Again, there's other ways to do it, but I personally find applying what we already been using might help you even see it to kind of connect it.
Can you explain why the negative signs are in those two equations we found that distance again?
Like right here?
Yes.
Well, what's the change in shear from the left side to the right side?
Okay, it's a negative.
It drops negative 42. Right? It starts at positive 42 and it has to get to 0.
Right.
You got to go negative 42. And then what's the area of the load curve? Well, it would be x times the load, but the load is down, and down is negative.
Okay. So, I'm sure if you get those mixed up, it'll change your answer.
Well, if you get it mixed up, you'll just end up with a negative x, and that won't make sense.
Right.
Okay? Any other questions about this one? We'll move on to Mr. Maxey.
I was going to say, if you have positive and negative shear that are both your maximum, do you want them both reported, or will just one number?
Well, in shear, all I care about is the maximum shear. Now, if I ask you what's the positive maximum, or positive shear, what's the maximum positive shear, then that's a different answer from what's the maximum negative shear. But really, in structural engineering, we don't really care. We just want the maximum shear.
But moment needs to be reported as positive or negative.
Yes. Because there could be a possibility where you'd have some negative moment, positive moment. If it was a concrete beam, you'd care about both of them. Okay. We'll stop that one. In case you're keeping score at home, that was the